Alright, so here are the examples for section 8.1, 8.2, and 8.3. What you should do is view the particular example and then go back to the PowerPoint until we get to the next one. Alright, so here's the first example in 8.1. That is finding critical z-scores for so that we can create our confidence interval. Okay. Suppose x bar is normally distributed. We know that 95% of all sample means fall within about 2 standard deviations of the population mean. That comes from the empirical rule. So we know if the x bar distribution is normal here, we know that about, here's our mean, which is mu, right? We know that about 95% of all the data fall within 2 standard deviations of the mean. So our goal is to figure out what this negative z or this z-score is here for this data point, and what the z-score is here for this data point. Okay. So to do that, all we need to know are the areas here and here. So how much area is in each tail? That means how much area is here and here. Well, we know that these areas have to be the same, right? Because the z distribution is symmetric. So let's think about it. We know that how much area is totally under the normal curve. Well, 100% of the area, right? So if you already accounted for 95%, that means that 5% fall within both tails. Therefore, 5 over 2% or 2.5% falls in one tail. Okay, so again, 2.5% there, 2.5% there, and then we complete 100. So now we're asked to find out what the z-scores are for this corresponding to this area. Okay. So if we want the standardized z-scores, all we need to do is use our calculator. We use the inverse norm feature of our calculator with the standard normal information plugged into it. Okay. So here we're going to go to second distribution. So remember that's at our vars key, so second distribution. And let's see, you can't really see that, can you? So our second distribution, we're going to go down to the third option. That's inverse norm. And so many of your calculators may not have that tail feature. But what we're going to do is put in our area to the left of the value that we want. So in this case, if we go back to our distribution here, let's put in this area to the left of this z value here. So that's going to be 0.025. Remember, we have to use a number between 0 and 1. So we've got to convert it to a decimal. So 0.025 or 2.5%. We're standardizing it, so we want 0 for mu and 1 for sigma. And we're going to paste that in there. Let's do that again. Okay. Looks like negative 1.96. So we had 0.025, 0, and 1 left. If you have an older model of the calculator, you don't need to put that in there. That's going to give us negative 1.96. Okay? So this is the leftmost z-score here. Left z-score here. this upper z-score, well, it's symmetric, so if 0.025% lies to the left of negative 1.96, then 0.025 area lies to the right of positive 1.96. So this guy's going to be negative 1.96. This one's going to be positive 1.96. Okay? So our z's, z criticals, are plus or minus 1.96. Okay? All right, so you can pause here and go back to the PowerPoint slides. All right, so here's example 2. This deals with constructing a confidence interval with sigma known. So that's, we know the population standard deviation. This is the procedure that we'll use. So here's our example. Julia jogs about 2 miles per day. The standard deviation of her times is sigma equals 1.80 minutes. She has a random sample of 90 of these times, with sample mean time x bar equal to 15.60 minutes. We want to find a 90% confidence interval for her overall mean time mu. Interpret your results. So here we're going to use, we need to first check to see if our conditions for the central limit theorem are met. And in this case, we need to know whether her her times for her runs are normally distributed, or we have a sample size bigger than 30. So here we have a random sample of 90. So n is bigger than 30, so we are good to go with using this formula to calculate this confidence interval. So recall the confidence interval formula. So our confidence interval can be obtained by using the formula x bar plus or minus our z critical times sigma over the square root of n. Okay? So note that this plus or minus is going to give us a range of values between x bar plus z critical times sigma over square root of n and x bar minus z critical times sigma over the square root of n. So what we need to generate are her x bar for her times, the z critical for the 90% confidence interval, sigma, and our sample size, right? So let's go ahead and gather those. We know x bar is equal to what? Well, 15.60 heat, right? So we know that's 15.60. Our z critical we'll find in a second. Sigma, we know, is 1.80. And n, the sample size, is 90. Now, to find z critical, we can, I have given you a table of all the z critical values in the PowerPoint slides, so you can just utilize those. Or if you forget that you have that, you can always generate it yourself. So we can find z critical by considering the normal distribution, right? So we are constructing a 90% confidence interval. So if we say this is z, 0, what we're trying to do is find the z values that trap 90% of the area between the two z values. So what's this z value? What's that z value? So again, to get those, we can just use the inverse norm feature once we know the areas here and here. Okay. So if, how much area would be in each tail if 90% is already accounted for? Well, there would be 10% cumulatively in both tails. Therefore, we would have 5% here and 5% there, or 0.05 as the area. So our z criticals can be found by using inverse norm of 0.05, 0, 1 left. Again, if you have an older calculator, you won't have this option. It will just give you the z-score for the left area. So let's see what we get there. Go to second distribution again, second distribution, inverse norm. Change our area to 0.05 this time, 0 and 1, and paste. So our z critical looks like negative 1.645. Therefore, our z criticals are plus or minus 1.645. Okay. Now we're ready to go to find the confidence interval. So we're just going to use that formula there to calculate it. So we know that her average overall time will be in between x bar minus z critical times sigma over root n and x bar plus z critical times sigma over square root n. Okay. So let's just plug in our values. X bar, so that's 15.60 minus our z critical 1.645 times sigma over the square root of 90. Same thing over here, just plus instead of a minus, right? So that plus or minus takes care of the plus or minus here from our z-scores. All right, all is left to do is just to calculate those values. 15.6 minus getting 15.29 and 15.91. So to interpret these results, we are 90% confident that Julia's overall average time is between 15.29 and 15.91 minutes. Okay. All right, you can go back to your PowerPoint slides now. All right, so here is the first example in section 8.2. This is dealing with finding t-values or critical t-scores for our confidence intervals when sigma is unknown. Okay, so we want to find the t-value such that the area under the t-distribution to the right of the t-value is 0.2, assuming 10 degrees of freedom. Okay, so let's try this out. If we want to figure out this t-value such that the area under the t-distribution to the right of that t-value is 0.2, it's a good idea to make a graph here. This is our t-distribution. Of course, again, we're using t because we don't know sigma. So here we want to find the t-value. 0 is our average. T-value such that 0.2 is to the right. So if 0.2 is to the right, our t-value is going to lie over here. It's going to be bigger than 1. So we know that 50% lies to the right of 0. So we know 20% is in here, 1.20. So we would like to know our t-score, our unknown t, which is here, so that this is true. So what we can do is use our inverse t function, inverse t, instead of inverse norm, okay? So let's investigate what our parameters are for that particular function. So we're going to go second distribution again. Go to inverse t instead of inverse norm. Okay? So if there's anything in there, just clear it out. All right, so notice here that we're just given the area and degrees of freedom for this one. Note that the area is always going to be the area to the left here, area to the left. So if we go back, we are given an area to the right, so we need to utilize the area to the left here to get our value. So if 0.20 is to the right, how much is to the left? Well, you guessed it, 0.80 is to the left, right? So we're going to use 0.80 as our area, and then with 10 degrees of freedom. Paste that in, and we get 0.879. So our t is t critical is 0.879. Right, we want to find the t-value for a 90%, let's say the t-values, for a 90% confidence interval with degrees of freedom 12. All right. So remember that with the confidence interval, we're dealing with the area between the two t-values, right? Between the two t-values. So let's draw that. 0 is our average. So 90% confidence interval, we're considering the area that's between the two with 12 degrees of freedom. So we're looking for plus or minus t-scores. What are these values here and here? Well, we can do the same kind of analysis. We need the area in the left and right tail. So here we have 5%, and here we have 5% as well. Okay? So again, if 90% is between the two, 10% is captured in both tails, therefore 5% is in each. So what we can do is use inverse t to find this t value, right? Because we need an area to the left. So inverse t of 0.05, comma, 12 degrees of freedom. So let's do that. Second distribution. Inverse t. This time 0.05 is to the left with 12 degrees of freedom. That gives us negative 1.78. Therefore, our t criticals are plus or minus 1.78. Okay. So you can go back to your PowerPoints now. All right. Here is the last example for 8.2. This is constructing a confidence interval with sigma unknown. Okay. So we know that there's a difference between what formulas we use when sigma is known and sigma is unknown. Okay. So the pasteurization process reduces the amount of bacteria found in dairy products. The following data represent the counts of bacteria in pasteurized milk in CFU per milliliter. for a random sample of 12 pasteurized glasses of milk. Assume a normal distribution. Construct a 95% confidence interval for the average bacteria count. Okay. All right, so again, the first thing that we want to do is always check the conditions on the central limit theorem. Either we need sample size bigger than 30, or it is assumed that the distribution which we're sampling from is normal. If we notice here, we have a random sample of 12 pasteurized glasses, so that's not bigger than 30. But if we assume a normal distribution, we should be good to go with our formula. Either of those two things must be true, right? So since we have this, we can use our confidence interval formula, okay? So we want to construct a 95% confidence interval for the average bacteria count, given some data this time, okay? So we have some data from 12 samples of so this is the random sample of 12. So this would be a sample of the glass. All right. Together, cumulatively they make up the sample. All right. So let's think about our confidence interval formula here. Confidence interval formula is x bar plus or minus. Now remember, sigma's unknown, so we're going to use t criticals this time. And the sample standard deviation and the square root of it, okay? So nowhere in the problem does it tell us anything about sigma. The best option that we have is to calculate the standard deviation from the set of data, okay? So recall how we do that. What we need our x bar, we need our t critical, we need our standard deviation, and we need our sample size. So the only thing that we have at the moment is n, right? We have n equal to 12, but nothing else. So we can just use our calculator to get these other three values, all right? So in order to get our average and standard deviation quickly, let's go and input these values into a list. So we're going to go to stat, which is there. And once we get into stat, we're going to edit our list. If there's anything in there, of course, go up, hit clear, push down, clear, push down. All right. So go ahead and input your data into list 1. Alright, so I have my data input into list 1. Sorry for the blurriness there. Okay, now we go back to stat, go over to calc, and we want the 1 var stats. The 1 var stats. So just hit enter, and enter, enter. And we get a list of all the statistics for those values. So you can see here that your x bar is 6.41. And our standard deviation S is 4.55. Make sure you're using the proper standard deviation. 4.55 is the sample standard deviation. Okay. Now all we need is our t-score for this particular problem. Okay. So finding t criticals. Of course, we want to do picture, use inverse t, right? So here is our t distribution, 0 is our mean. And we're doing a 95% confidence interval, so 95% is between each of the unknown t values that we want. We want this t and this t, right? So we need the area here and here. So if 95% is trapped between the two, then 5% is outside in the tails cumulatively. So that means 2.5% is here, 2.5% is there since we're symmetric. So we can use our calculator to generate this t-value, which should be negative, and then we'll just put a plus or minus on it. So inverse t of 0.025, comma, now we need our degrees of freedom. Recall that the degrees of freedom is n minus 1, so that would be 11 in this case. So let's see what we get. We're going second distribution, inverse t, 0.025 with 11 degrees of freedom this time. So negative 2.20. So our t critical values are plus or minus 2.20. Okay. So again, we're going to use our formula to make that range of values for our confidence interval. Okay. So for the lower bounds, it's going to be x bar, that's 6.41, minus, it's the lower bound now, 2.20 times 4.55 over the square root of 12. Let's see what we get. Getting 3.52. The upper bound is 6.41 minus, plus 2.20 times 4.55 over the square root of 12. Calculating that, we'll get 9.30. 3 rounds. So again, what does this mean? We're creating a confidence interval for the average, the overall average bacteria count, right? So we are 95% confident that the average, the overall average bacteria count is between 3.52 and 9.30 CFUs per milliliter. So again, we are 95% certain that the true average bacteria count after pasteurization is between these two values here. All right, you can go back to your PowerPoint, so you have one more section left. All right, so section 8.3 deals with confidence intervals for a population proportion rather than a mean. So here we'll construct a 95% confidence interval for P, the population proportion. So it says, suppose we cure 900 of 1,000 heartworm-infected dogs. What is the reasonable range for the cure rate P of our new treatment? Use 95% confidence. Okay. So here we need to use the appropriate formula. Remember, now we're dealing with a population proportion. So the confidence interval formula for that is P hat plus or minus Z critical times the square root of P hat Q hat over Again, Q hat is just 1 minus P hat, right? So what we need are P hat, Z critical, and N. So right now, N is 1,000. That's our sample size. P hat is obtained, it's the proportion of the cured dogs, right? The proportion of cured dogs would be 900 out of 1,000, which is 0.9. Q hat would be 1 minus 0.9, or 0.1. And we need a Z critical for 95% confidence. You can just use the table, or again, if we want to find the Z critical, set up your normal distribution. Z is 0. 95% lies between. So how much area is in each? 2.5%. Okay. So to get these unknown z's, we'll need to use inverse norm. Remember that we're using the z distribution for proportions, so we need to use our inverse norm feature. 0.025, 0, 1 left. Okay. So let's do that. Second distribution, inverse norm. 0.025, 0, 1 left. Gives us negative 1.96. So our Z criticals are plus or minus 1.96. And now we're ready to go. So so P, we know, will be in between P hat minus Z critical root P hat Q hat over N, and P hat plus Z critical times P hat Q hat over N squared root. So let's put in those values. P hat is 0.9 minus 1.96 root 0.9 times 0.10 over 1,000, less than the true P, less than 0.9 plus 1.96 root 0.90 times 0.10 over 1,000. So let's calculate it. P is going to be in between what numbers? So our lower bound is 0.88. Plus 0.92 if we round to 2 decimal places. Therefore, we are 95% confident that between 88% and 92% of all dogs will be cured of heartworms with the new treatment. So again, these are proportions, or you can change them to percentages. And we always spin our interpretation in the context of the situation. So again, we want we just don't want to say P is between 0.88 and 0.92, but we want to relate these values back to the overall situation in terms of infected heartworm-infected dogs. All right, so that does it for this lecture. You can go ahead and try the suggested homework problems.